let's head on to the last of our preliminary discussion, which is the implicit differentiation. Now in this topic, we will be discussing all about the implicit equations and how we differentiate these kind of equations or functions. So before anything else, let us first identify what is an implicit equation and how does it differ from an explicit equation or function. The ones that we've been solving ever since we started differentiation are called explicit functions or explicit equations. That is, if we would look at the form of the equation, we could see that we have y here, y is equal to f of x is equal to something, and in this form we have something like y is equal to f of x. You have y here, just the y, and then some pure function of x at the other side of the equation. And since this is x squared plus x is equal to y, we can actually do something like rearrange this in a way that this is y is equal to x squared plus x. It's just that we have written x squared plus x, but it is still equal to y. So whenever the form is like this, y is equal to some function of x, then these are called explicit functions. And now usually when we talk about implicit equations, these are the equations in which at the same side of the equation you would see a function that is, or a relation that is expressed in x and y, in such a way that it is not just y but x and y. It could be just y, but for example, y has an exponent that is greater than 1, so that's not just y, that's y to the n. So for a case like that, that's also an implicit equation. So implicit equations are actually easy to identify because if you would look close at this equation, you can see here that x squared plus y squared is given in a way that they are mixed in the same side of the equation. So we call this implicit, unlike this one. Now, especially for this one, x and y is seen in just one term here, and they're just multiplied. So you can see here that these are implicit equations. Same as this one, though we can rewrite this as x plus y and then minus xy, just to see that the whole term here, or the relation here, has some function. It's a function of x and y. And then lastly, we have here, even though this is rational, you can see that there's this x and y term at the side of the equation. Now, sometimes implicit equations can be made explicit. For example, this x squared plus y squared is equal to 1. In cases like this, we have something like this equation, and then if you wanted to make like explicit equation from this, we have to isolate y from all these equations. So we can say that this y squared is equal to 1 minus x squared. And if we just need this y here, and this is y squared, we can take the root of both sides of the equation, and then what we'll be having here is the positive or negative square root of 1 minus x squared. So in this case, this is already what we call the explicit equation of this form, but not in all cases we can made an implicit equation. Not in all cases we can make the implicit equation explicit. Just take for example this, let's say we have y squared plus 3y, and then let's have some plus 4y to the 5th, and then add some x, and then let's equal it to 4. So in this manner, we could just simply transpose this x, and we will just have y here. And probably you'll be thinking, okay, we have already isolated y there, so it's already done. But the thing is, this is in square, this is in the first degree, and this is in the 5th degree. What we need is just simply the y term, and then equate this to some x. Now from this, you may try factoring out y, so you'll be getting y, and then y plus 3 plus 4y to the 4th. That is equal to 4 minus x. Now, if you would be rewriting this as y is equal to something like 4 minus x all over y plus 3 plus 4y to the 4th, then this is still an implicit equation, simply because yes, you have a numerator that is in terms of x or function of x, but as you can see here, there's just these y variables here, and this one is really difficult to like give something like a relationship wherein you could express this as on the sole function of x. That's why sometimes the equations cannot be made explicit. That's why when you have a function that can't be made explicit and you need to like find the slope of that function, that's when implicit differentiation comes in handy, because you can actually find the derivative without transforming that to explicit equations. The restrictions are that, of course, not all equations can be made explicit, so you will do implicit differentiation. But if you find it easy to like do some equation to be made, if you find it easy to like transform an equation to explicit and then easier for you to differentiate that, then that'll be no problem. But there are some instances that it is a lot easier to solve for an equation in its implicit form. Now, to understand better, let's just take this first here, x squared plus y squared is equal to 1. That's actually an equation of a circle. Just to explain a little about this implicit differentiation. Now, remember, we're differentiating. Before we start differentiating this, let's have some review of your differentiation of explicit equations. So, for example, we have y is equal to x squared plus 2x. And we usually differentiate it as if the derivative here would be something like 2x plus 2. And we're all done. But on a deeper meaning, on a deeper level, it's just that what happens is that we take the derivative of both sides with respect to x. So in that way, and you can see this expression as if this is the Leibniz form or notation. But what I'm concerned much more about is this the derivative of x with respect, the derivative of y with respect to x. And this derivative of y with respect to x, we represent that as dy over dx, and then the derivative, which is simply 2x plus 2. Now, we used to have something like, in the Leibniz notation, I used to tell you that this should be 2x plus 2 and then dx. That is provided that we don't have an expression for this one. But since we already have this dy over dx, then that is equal to the 2x plus 2 only. And as you can see here, this y, it is differentiated with respect to x. That's why you have dy over dx. This simplifies further to y prime if we have some independent and dependent variable in essence. So that's how it goes for our derivative. In that manner, the derivative of y is simply 1, and then y prime would be the dy over dx, which simplifies, or which implies that you have differentiated y. So in this case, if I would take x squared plus y squared is equal to 1, that is this one, we will be differentiating. If you have something like explicit function, you just have to differentiate that the same side of the equation with respect to x. Or of course, if the problem specifies that you have to differentiate that with with respect to a certain variable, then that will be different. But usually it's x. So you should be taking the derivative of the whole equation with respect to x. And if you take the derivative of this with respect to x, that is simply just 2x. And then there are two ways we can solve this. So the derivative would simply be 2x and then plus the derivative of y squared. You'll be applying the same principles as how we differentiate x. In this case, if we would assume that this is x, that will be just 2x. So, but in this case, it's y. So if you differentiate y squared, that will be 2y. But it doesn't end there. Whenever you differentiate y, you attach y prime to any differentiation that you do with y. So that's a rule for implicit differentiation. And this one is equal to 0. So the only difference here is that we're like differentiating all of the variables x and y, and then you attach the y prime to every differentiation that you do with y. And then finally, we usually rewrite the equation in terms of y prime. So in this case, if we have y prime, that is equal to, I would transpose this 2x to the right side, that would be negative 2x, and then divide this by 2y. So the derivative using implicit differentiation would be negative x over y. And during implicit differentiation, what you can usually see is that our answer would be a function of x and y, and that's perfectly normal to see in implicit differentiation. Okay? And what if I ask you about how do you rewrite this in terms of Leibniz notation? So you'll just have to write dy over dx that is equal to negative x over y. So that's how it goes for implicit differentiation. There's another way of doing this, and this is something like an introduction to how we do it in differential equation, which is you'll be taking after integral calculus. So instead of writing y prime, what you can do here is that if we take the derivative of this with respect to x, so 2x would be something like 2x, and then differentiating x would give us dx. So once you differentiate a variable that is x, you add something like dx, which is the differentiating variable, and then for y, we have 2y, and then you add something like dy, and for constant that would be 0. So in this case, we have dx and then dy, and we need to find this dy over dx so that we have something like y prime. So in that case, I'll be taking this 2x over dx to the right side so that I have this one, and then so that I will have dy over dx, I'll be dividing both sides by 2y. So in this case, I have dy that is equal to negative x over y and then dx. But since I need dy over dx, I'll be dividing both sides by dx. And that way we can cancel this, and then we're left with the same answer, dy over dx is equal to negative x over y. So these two are the same. So that's how it goes for implicit differentiation when you use something like dx and dy to represent the change that you do, or the derivative that you do with the variable that is presented. So it's up to you what to use. It's just a matter of perspective which you find easier. And for me, I do a lot of interchanging whichever is easier, but I usually prefer this one simply because y prime is a lot easier to write than dx and then dy. But during differential equations problem, you do this. Of course, that's dE. So you don't have to like worry about your writing. Just follow these rules and you should be getting the same answer. But I would always say that do the things that you are more comfortable with. Okay, so let's try doing this this number 2 here. By the way, it's just an example. I just wanted to show you how this works, and the only thing that is different to this implicit differentiation is that we have something like added differentiation with y. So again, what we have to do is to differentiate both sides. So you can actually write this expression like this, and then that is the derivative of 3. So of course that will be the derivative with respect to x. If it's not, for example, it's the derivative with respect to y, that would be like very uncommon. But if the instruction says if the instruction tells you that do it, then of course you'll be doing it. So that will be d over dy, but it still it's much less common. So let's try differentiating this, and this one is in x and y multiplied. And remember, since these are two variables that we'll be differentiating, what we'll be applying here is, of course, what we call the product rule, because x and y are different. So in this case, if I'll be differentiating x times y, I will be getting x just for the first one, and then the derivative of y. And the derivative of y is simply 1. But since I have differentiated y, I need to add something like y prime. For the sake of this problem, let's just add something like 1 and then y prime. And then I'm doing product rules, so I have to add and then copy y, and then the derivative of x is simply 1. So in this case, the derivative of xy, so let's have something like this is the derivative, or I'll just write something like the derivative of xy is this term here. And then we proceed with the next one that's positive, and then xy squared sine x. Now this is much more complicated because it is a multiplication of like three variables here. I mean, yeah, three functions. But we can take on x sine x as 1 and then y squared. So we have x and then sine of x and then multiply it with the derivative of y squared. That is simply 2y, and then of course we add y prime. So we're done with the first part of our product rule, and then we add x, and then we add y squared, and then we multiply this with the derivative of x sine x, which is also a product rule. So in this case we have x times cosine of x and then plus sine x times, we multiply this with 1 since that is just x. So finally, what we have here, and that is of course equal to 0 since the derivative of 3 is equal to 0. So in that way I can also rewrite this as x y prime, since these are just the, simplifying. So plus y and then plus, this can be rewritten as 2xy sine x and then y prime plus, we can expand now here, so xy squared cosine of x, and of course have the habit of like writing x first before y, and then plus, since we have here y squared and then just sine of x and then equal to 0. And by this form we've already obtained the necessary differentiation, and we just need to like isolate y prime from all of these and then give the expression in terms of y prime. So the derivative would be equal to, let's just factor out y prime from the functions or the terms that there is a y prime. So in this case we have here 1, so that's x, and then in this case we have y prime, so that's plus 2x y and then sine of x, and then the rest we don't have any y prime, so we transpose that to the right. So what we'll be getting is negative y and then minus xy squared cosine of x and then minus y squared sine of x, and then we divide all of that with what's multiplied with the y prime just to eliminate it and just to have y prime at the left side alone. So in this manner the answer here is y prime, and then this, so the answer here will be y prime is this whole term here. So let me just add the negative here in front of the fraction line so that I can make all of these positive, so that it's more pleasing at the eye probably, but that's just your own perspective, so you don't have to like do that also. Okay, so this is your answer for the implicit differentiation of that particular equation here. So you can also, that is also equal to, this y prime is also equal to dy over dx. So you may also want to write it like that, but it all depends on how you interpret this. By the way, you can also use this form wherein when you differentiate x, you would be writing something like dx and then dy, but of course it will be much easier for you to use y prime, especially when the equation gets longer. So that's it for our implicit differentiation, and let's try having some more. For example, this one, I think, let me just give you one. Let's try having something like x over y and then plus cosine of x plus y, that's equal to like y. So let's take that for example. So for implicit differentiation, we just have to take the derivative of this with respect to x. Of course, that will be instruction for you on what to do. It's just that I'm generalizing that you'll be taking the derivative of the function with respect to x. So let's do this. And in this case, I'll be doing something like the Leibniz notation for x. So I'll be using dx and dy instead of just y prime. So now I can do this, and then we have y, and then the derivative of x would be dx, and then minus x, and then derivative of y would be dy, because that's 1 dy, and then y squared. So I did the product rule in this section. And then plus the derivative of cosine of x plus y would be negative sine of x plus y. And then of course you need to differentiate x plus y, that will be dx plus dy. And then that will be equal to dy over dx. And what you need here is to simply take in on dy and then dx to all of this, and then probably we could give the expression in terms of y prime alone. And this is equal to the derivative of y would be dy. So what we have to do here is to segregate this dy and dx in a separate side of the equation. So I'll be taking dy at the left side. So we have negative x dy over y squared, and then transpose this dy here, so I have negative dy. And then we have some dy here, but it is multiplied with the sine of x plus y, so that will be negative sine of x plus y, and then multiplied with dy. That's also equal to what's left here, and I'll be transposing that to the right. So I'll be left with sine of x plus y, and then dx, and then I think there's one here, the y dx over y squared. And it simplifies further to 1 over y. So I'll be having 1 minus dx over y. So in this case, I've already separated all the things that we need here, and then I'll be factoring out dy from the expression. So I have dy and then negative x over y squared minus 1 minus sine of x plus y. And then that is equal to dx multiplied with sine of x plus y, and then minus 1 over y. And in this case, since I need dy over dx, I'll be dividing both sides by dx. So I have dy over dx, and since I just need this dy over dx, I'll be dividing the whole expression with this. So the answer would be sine of x plus y minus 1 over y divided by, that's negative x over y squared minus 1 minus sine of x plus y. So this is our answer for this problem in terms of the Leibniz notation that we have. Now, implicit differentiation is very helpful in finding the slope of a certain equation. So if we have a problem, let's say find the slope of, let's say, x squared plus 4xy minus 3x equals 67. Let's say at x is equal to 4. So this is the problem. You need to find the slope of this function that we have at x equals 4. And when we do this, what we need to do is to understand that the concept of the slope is that you find the derivative of the equation, and that's just saying that you need to take that y prime that will be equal to the slope. So in this case, I'll be taking the derivative of x squared plus 4xy minus 3x equals 67, and then take that derivative, both the derivative of that. So what we'll be having here is simply 2x, and then plus, we have 4x times y prime plus y times 4, and then minus 3, that is equal to 0. So in this case, if I just need this y prime, because that's the slope, so y prime is equal to something like 3, and then minus 4y minus 2x, and then divided by 4x. So I just technically rearranged all of these, and this is my final answer for the slope. But as you can see, this is just the equation of the slope. I actually need the value of that slope, and it says here that at x equals 4, I need to find that slope. So for example, I have a graph of this function, and this is, for example, it looks like, let me just, for example, it is like an ellipse, but I'm not saying that this one is ellipse, I just assume that this one. And let's just, oh no, it's not an ellipse, but let's try having something like a parabola that opens diagonally. Though this is not actually the exact figure, I just wanted to give you an idea of how it goes with this. So for example, I need to take the value at x equals 4, so 1, 2, 3, 4, and then somewhere here it has a y value, and I need to find the slope somewhere there. And the derivative gives me the equation for the slope. I just need to find the values of x and y there and then substitute it. We already have the value of our x, and that's 4, but we need to find the value of y. So with that, we need to substitute the value of y, the value of x, so that we can find the value of y in our equation here. So in this case, let's have something like 4 squared plus 4. This is the original equation. I'll be substituting 4 so that I can find the value of y. Since I need an ordered pair here, x, y, to substitute from the values here of our slope. So, because if you just be substituting x equals 4 here, you'll be left with something like y here, and that doesn't give you a value that is a real, or a constant value. Alright, so we have y and then minus 3 times 4, that is equal to 67. So upon calculating, I'll just be using some calculator, and what you'll be getting there is a value that is around 3.9231. So to give you an exact value, that will be 51 over 13. So in this case, since we already have x and y, so the point here would be 4 and then 51 over 13, and that's an incorrect assumption of the point. That should be here, but I just told you that it's just an assumption. So what is important here is just to find the value of y prime. So y prime here is simply the derivative which we obtained through implicit differentiation, and then substitute the value of x and y. So 3 minus 4, and then the y here is 51 over 13, and then minus 2 times 4, and then divided by 4 times 4. So now we have the slope at that point for this equation that we have. So the answer here is negative 269 over 208. So this is the slope for this equation. Okay, and that's a negative slope, so the line should be going downward, since that's a negative slope. So you might be wondering why before we used to something like solve for an explicit derivative, and then there's something like this at x is equal to some kind of value, and then you already have the value for your f of x, which is a constant. And that happens because the function is actually explicit. So when it is explicit, you just have to specify the value of x, and then you can substitute that, then you're done with the slope. You can already have the value of your slope for that. But since we are talking about implicit functions here, so the derivative would be expressed in terms of x and y, so you still have to find the pair of that, and you'll be able to get the pair of that from the original equation. You substitute the value of this given domain, and then you'll be able to find the y value for that. So I think that's all for the implicit differentiation. So I hope you understand that the concept of implicit functions and its relation to explicit is that implicit functions are the much complicated types of equation in which we express a certain value that is in terms of x and y, or several variables that we have. And differentiating implicit equations would give us the implicit derivatives, where we can express the derivative in terms of two variables or multivariables. Substituting the value of that would give us values of slope or whatever is applicable. For example, if it's speed or velocity or acceleration, it depends. But the thing is, explicit equations would just need a value of x to solve for the slope if we're talking about graphs. But for implicit equations, we need the x and y values so that we can solve for the slope of that particular equation or graph or function. So the application of implicit differentiation is very evident when we'll be discussing all about the applications of the extremal values that we'll be discussing on the midterm. And the higher order derivative that I used to mention before will be also using that idea to generate graphs and points from this certain kind of equation. This is just something like an introduction that I will be giving you, that differentiation can give you the solution to finding the slope of a certain kind of graph or equation, because that's how we derive derivatives before. Okay, so I think that's all, and let's have some synchronous class just to address all of your issues and the things that are boggling your mind about these topics. Okay, so see you.